Yesterday, we were looking at total differentials. So we say that sometimes we have a function z that is in terms of two variables x and y, and x and y are also variables of some other parameters, let's say u and v. We had the equation of how we work out the total differential. So let's continue with exercise 2.5. We were on number 1. So we had to work out. Somebody's saying something. I can't hear you.
Yes, I'm saying something. Before we continue, ma'am.
Hey, I can't hear you. Very soft.
Can you hear me now?
Yes, I can hear you now.
Okay. What I was saying is, before we continue with today's class, may I take you back to yesterday's class?
Okay.
There's something from yesterday's examples, the first one. On total derivatives.
Yeah.
Okay, quickly go to the next page. Yes. When deriving XR,
Yeah.
wasn't it supposed to be 2x e to the power of r cos theta minus e to the power of r sine theta?
When we're differentiating x with respect to r.
Yes.
When we differentiate x with respect to r, the answer is e to the power of r cos theta.
Okay. But what about differentiating the cos theta, man? Like using the product rule.
Why would you use the product rule? Okay, so like I was saying, we have to differentiate z with respect to v this time. So we'll follow a pretty much similar formula, except here we differentiate with respect to v and over there. So z with respect to v, this is zx xv plus zy and then yv. So this zx, we've already worked it out. It is this one here. So we just rewrite it. So y e to the power of xy, and then x with respect to v. This is 1 over uv multiplied by u, which leaves us with 1 over u. No, 1 over v. Let me just write it. So it's 1 over uv multiplied by u. So we have u over uv. And then z with respect to y, we differentiated it, it's there. So we have x e to the power of xy. And then y with respect to v, this is minus sine of uv, and then we multiply by the derivative of uv, which is u. Okay, then simplifying as far as possible, you can see that the u's here will cancel. So we have y over v e to the power of xy, and here it's not a plus because of this minus over here. We'll have x over u e to the power of xy sine of uv. Okay, so again, just using the formula and substituting appropriately. Okay, let's move on to number 3. We have z to the power of 4. Not z to the power of 4. Z is equal to x to the power of 4 plus 2x squared y plus y to the power of 3. And then x is our cos theta and y is our sine theta. So we have to differentiate z with respect to r as well as with respect to theta. This is on page 25. Okay, so doing that, z with respect to r, first I must differentiate this with respect to x, so that is 4x to the power of 3 plus 4x times y, and then I multiply by r differentiated as not r, x differentiated with respect to r, which is cos theta. And then z differentiated with respect to y, so this is 2x squared plus 3y squared, and then we multiply by y differentiated with respect to r, which is sine theta. Okay, there isn't much that multiplying out the brackets will do, so we can just leave it like that. And then z with respect to theta. First we have z with respect to x, which is 4x cubed plus 4xy, and then x with respect to theta, that's minus r sine theta. And then z with respect to y, this is 2x squared plus 3y squared, and then y with respect to theta, which is r cos theta. Okay, don't need to multiply out the brackets, but we can write the positive term first. So we have 2x squared plus 3y squared r cos theta minus 4x cubed plus 4xy times r sine of theta. Okay, so that is our answer. Then number 5. Z is equal to e to the power of 2x plus 3y. X is r hyperbolic cos of z, and y, sorry, not z, that's t. And y is r hyperbolic sine of t. So we want to differentiate z with respect to r. First, z with respect to x. So So that will be 2 times e to the power of 2x plus 3y. And then we multiply by the derivative of x with respect the derivative of x with respect to r, which is just hyperbolic cos of t. And then we add the derivative of z with respect to y, which is 3 e to the power of 2x plus 3y, and multiply by the derivative of y with respect to r, which is hyperbolic sine of t. So you can see not very difficult derivatives here. You just need to know how to substitute them in the formula. Then z with respect to t. First it's z with respect to x, which we've done already, 2e to the power of 2x plus 3y. And then we multiply by the derivative of x with respect to t, which is r hyperbolic sine of t. And then y, z with respect to y, which we did already, e to the power of 2x plus 3y, and then multiply that by the derivative of y with respect to t, which is r hyperbolic cos of t. So this is r. Okay, and again, there's no need to rewrite it, or you can factor out the e to the power of 2x plus 3y, might make it shorter, but not really going to make that much of a difference. Okay, then the last one there, number 7, we have z is ln of x to the power of 3 plus y to the power of 3. X is e to the power of u minus e to the power of v, and y is e to the power of u plus e to the power of v. So we want z with respect to u. So we start with z with respect to x. So that's 1 over x cubed plus y cubed. And then the derivative of x cubed plus y cubed, which is 3x squared. So in the numerator, we'll have 3x squared. And then we multiply this with the derivative of x with respect to u, which is e to the power of u. We add the derivative of z with respect to y. So here we'll get 3y squared over x to the power of 3 plus y to the power of 3. Then multiply the derivative of y with respect to u, which is also e to the power of u. Okay, you can write this as a single fraction because our denominators are the same, and even factor out e to the power of u if you like. So e to the power of u, 3x squared plus 3, or even factor the 3 out. I have 3x squared plus y squared over x to the power of 3 plus y to the power of 3. And then with the other one, z with respect to v. First we have z with respect to x, which is this one got in the previous step. So we have 3x squared over x cubed plus y cubed. Then we multiply by the derivative of x with respect to v, which is negative e to the power of v. So this is negative e to the power of v. And then we add the derivative of z with respect to y, which is this one here, 3y squared over x cubed plus y cubed, multiplied by the derivative of y with respect to v, which is e to the power of v. And then again, like we did in the previous step, you can factorize and combine it as a single fraction. So this will give us a denominator x cubed plus y cubed. The 3 can be factored out, e to the power of v can be factored out, and we have y squared minus x squared. Okay, so that is it on total derivatives. As usual, any questions that I don't do in the exercises, do them. It's good for you to practice. The good thing with the book is that you have the answers at the back, so you can see if what you've done is correct or not. So what we are supposed to look at today is the rate of change and small increments. Okay, and with this rate of change, what we do is we actually make use of the formula of the total derivative. So we look at situations where one of the variables is changing at a certain rate, and we want to work out how does that affect the other rates of change. So for example, if you have a balloon, you're blowing let me see, you're blowing air into the balloon. Now the way the radius changes obviously affects the way the volume changes. So at a certain point, the radius may be changing at a given rate, and the rate that the volume is changing is affected by the rate at which the radius is changing. Okay, but the way we solve these questions is simply by using the total differential formula. So we have our usual formula dz dt. So you have z changing with respect to time. We find the change z with respect to x, and here dx dt. So here x only depends on t. That's why this is a total derivative instead of a partial, like we did in the previous total derivatives. But again, you can see it's like this x cancels, and you're left with the change in z with respect to t. And you also include dz dy times dy dt. So again here, this is a total derivative, a full derivative, because y only depends on t. So most of the questions in this section are supposed to be somewhat realistic, so things that you can imagine instead of just equations with variables. So the first one is, look at an example. So the first one is we are given a right-angled triangle. So we have a right-angled triangle, and this is zxy. That is what the triangle is called. And we are told that the two short sides, x and y, decrease at 2 centimeters per second, and increase at 2 centimeters per second and decrease at 3 centimeters per second respectively. So we have a right-angled triangle like this. So we have shorter sides. You can call this one x, this one y, and then our z is over there. Now we are told that x is increasing, so the x is going that way. So the triangle is getting longer in that direction. But then y is decreasing, so it's going that way, it's going down, so it's getting shorter. So this is what your original triangle looks like. Then after a while, it'll look something like this. So you can see the y has decreased, the x has increased, and then again, something like that, and it continues in that manner. So your x is increasing and the y is decreasing. Now what we want to do is to work out the rate at which the hypotenuse, because obviously you can see if x and y are changing, then z is obviously changing here. It's like the hypotenuse, I don't know, getting smaller, longer. There is a change that is happening in the hypotenuse when both of these are changing. So we want to find out when x is equal to 5 centimeters. So x starts at some number, maybe it was 7 centimeters. Now we measure x when x is 5 centimeters, and at the same time y is 3 centimeters. We want to find out when x is 5 and y is 3, at what rate is the hypotenuse changing? Okay, so when you're given the question like this, if possible, draw a sketch just to illustrate what it is you are working with, have a better understanding, and then write down everything you're given. So we're given x is equal to 5, y is equal to 3, and we're also told that x is increasing at a rate of 2 centimeters per second. So that is the change in x with respect to time. So we say dx dt, this is equal to 2 centimeters per second. Then we are also told that y is decreasing. So when something is decreasing, we say that the rate is negative. We'll use a negative rate. So we say dy dt, this is negative 3 centimeters per second. So the negative implies that it is decreasing. When your rate is positive, it means your rate it's increasing. When the rate is negative, it means that you are decreasing. So you can say it's decreasing at 3 centimeters. So using the word decreasing represents the negative, or you can just say the rate is -3, and then from there you can know that the negative implies that it is decreasing. So we write down the information that we are given in the question, and then you come up with an equation that relates all your variables over here. Now this is a right-angled triangle, and we know that in a right-angled triangle, z squared is equal to x squared plus y squared. So this is the equation that relates all these three variables. Okay, and then what we are asked to find, what are we asked to find? The question says determine the rate at which the hypotenuse is changing at the instant when x is 5 and y is 3. So we want to find the rate of change of z with respect to time. So this is what we are looking for. How fast is z changing with respect to time at this instant? Okay, so we have the equation that relates x and y. Now we need to come up from this equation with dz dt. We will substitute everything that we have, and then from there we can solve for dz dt. So when we have z squared is equal to x squared plus y squared, this means obviously that z is the square root of x squared plus y squared. Okay, and then we can work out the total derivative like we did in the previous section. So dz dt this is the partial of z with respect to x multiplied by dx dt plus the partial of z with respect to y multiplied by dy dt. Okay, now because we're looking for the rate of change of z with respect to t, this dx and this dt are just they are numbers, so we'll just substitute those numbers which we have over here, 2 and minus 3. All right, this nicely. Okay, so we know what z is. We can work out the derivative of z with respect to x. So this is a half x squared plus y squared to the power of minus a half, then multiply by the derivative of the inside, which is 2x, and then we still have our dx dt. Then the same thing, z with respect to y partially. This is a half x squared plus y squared minus a half times 2y, and then dy dt. So we can see that the half and the 2 will cancel, same thing over there. So dz dt, this is just x over the square root of x squared plus y squared, dx dt plus y over the square root of x squared plus y squared times dy dt. Okay, and now we just substitute. We know from the question that x is equal to 5, y is equal to 3, dx dt is 2, dy dt is negative 3. So it's just substituting now. So x is equal to 5. So we have 5 over the square root of 5 squared plus 3 squared, because y is 3, and then multiply by dx dt, which is 2. So it's changing, it was increasing at 2 centimeters per second, and then y here is 3. Divide this word 5 squared plus 3 squared, and then multiply by dy dt, which is negative 3. So this you just do on your calculator, and I got the square root of 34 over 34, which is 0.171, and this is in centimeters per second. So that tells us when you have a right angle triangle where the x value is increasing at 2 centimeters per second and the y value is decreasing at 3 centimeters per second, when you get to the point where the measurements are x length is 5 and the y length is 3, then at that point the rate at which the hypotenuse is increasing is 0.171 centimeters per second. So we can write the hypotenuse is increasing at a rate of 0.171 centimeters per second at the instant when x is 5 and y is 3 centimeters. Okay, so that's what we have. So here with these rates of change, we're looking at instantaneous rates of change at that very instant. And most of the time, yeah, anyway, it's an instantaneous rate. not necessarily that that is how it is moving the entire time. Okay, then number 2, we are told that a conical reservoir has a radius of 5 meters, and it has a height of 15 meters. Then it contains water that is flowing out at a rate of 1 meter per second squared. So the water is flowing out. That means the volume is decreasing. So that means that dV dt is -1. Meters per second squared. Let's say dV. Meters cubed per second. Then we say, at what rate does the water level decrease when the depth of the water is, at what rate does the water level decrease when the depth is 3 meters? So as always, draw a sketch. You have a cone like that. And I'll copy this question right. Let me just see. Okay, yeah, it's fine. Right, so we have the radius here. Which is 5, and the height of the cone here is 15, and these are all in meters. Okay, and what we are looking for is at what rate the water level decreases. So when we're talking about the water level, we're talking about the height, because whatever level the water is, that is the height of the water in the cone. So we're looking for dH dt. So dH dt, this is what we are looking for. So you can imagine some water in there. It's flowing out. Okay, so now what we do is we come up with an equation to relate all our variables. So we know that V is equal to a third pi r squared times the height. And if we were to differentiate this V, we find the total differential, we would have a part that includes dr dt, but we don't have dr dt in the question, so we have to try and get that from the information that we are given. So here, at whatever level the water is, let's say the water is here, that is the level of the water. Because of our similar triangles, the radius here, this little radius that we will get here, compared to the height over here, those two are actually proportional to the radius here and the height over there, because the cone is consistent. So what we mean by that is that the radius over the height at any point, radius over the height at any time. So whether the water is here or it's there, if I take that new radius divided by the new height, that will always be in the ratio 5/15. And this 5/15 is the radius of the cone, the way it is, and the height of the cone, the way it is. So it remains at the radius and the height have a constant fraction. So from here I can work out R. So this means that R is equal to h/3. Okay, so if R is equal to h/3, I can use that to work out dr dt. So from here, dr dt, this is equal to 1/3 times dh dt. So you just differentiate both sides. So here, differentiate with respect to t, differentiate with respect to t, and the 1/3 is a constant, so it doesn't affect your derivative. Okay, so if one function is a constant multiple of the other, if you want to work out the derivatives, you just differentiate normally and then multiply by your constants. Okay, so even though I'm not given dr directly in the question, I can figure it out. And then now over here, I work out the total differential. dv dt is equal to dv dr multiplied by dr dt plus dv dh times dh dt. Okay, so dv dt, yeah.
If we ask questions like these ones, ma'am, will we be given the formula of like the volume of a cone or stuff like
No,
that?
we expect you to know the volume of a cone. Okay, so dv dt, this is dv dh. Well, I'm sure if it's like some complicated shape that we don't regularly use, you may get the volume or the formula, but cone, a sphere, a cylinder, those ones we expect you to know them. Okay, and then we multiply by dh dt, and this dv dr times dr dt. Okay, so again, remember dr dt is just 1/3 of dh dt. Now what we're looking for is dh dt. We have everything else except dh dt. So we say that dv dt, this is dv dh, and this one is 4 dh dt, dv dr, and then here, because I don't have the actual value of this, I replace it with the one I got from r/h, which is 1/3 times dh dt. Okay, so I can now substitute here my dv dt. We know this is equal to -1. That's given to us in the question. Then, okay, maybe let me work out everything and then substitute at once. This is just dv dt, and then dv dh, I differentiate the formula for the volume with respect to h. So I have 1/3 pi r squared, and then times dh dt, and then the 1/3 will come out here, and I multiply by dv dr. So differentiate V with respect to R. The 2 will come down. You have 2 pi RH. We have 2 pi RH. That's dV dr. And then you multiply by dH dt. Okay, so you can see where I'm going. I want dH dt to be the subject of the formula, so I'll have to factorize here and then divide by these terms over here. So dV dt, let me factor out dH dt, which is what I'm looking for. So I have 1/3 pi r squared, and then over here I have 2/3 pi r times h. Okay, and this means that dH dt is dV dt divided by this big fraction over here. So it's 1/3 pi r squared plus 2/3 pi r times h. Okay, so I have everything I need. dV dt, we said it's -1, it's given in the question. And then 1/3 times pi. Then the radius is 5. That's no, that's not the radius. Let me just read the question. Okay, the depth is 3, so we use this formula R/H is equal to 5/3 to work, is 5/15 to work out what R is. So here we only know that H is, so we're looking for the instant when H is 3. So we can work out R. So R, we use this formula over here. R/H is equal to 5/3. So we have R/3 is equal to 5/15. So this means that we have 3 times 5/15, which gives us 1. Okay, so we're using this relationship over here. Okay, so now I have everything that I need. So times r squared, which is 1, and plus 2/3 times pi times 1, and then our radius is 3. Okay, that will work out on your calculator. Okay, let's see, -1 -3. over 3 pi. Okay, I'm getting negative 0.136, and this is, what are our units? Sorry, the units are meters per second. Okay, and it's negative. That tells us that it is decreasing. You just see if everything is all right here. Okay, dVdh. Then third 2 pi. Okay, I see here. Okay, yeah, that's why. I think here the derivative is not correct. No, I think it's fine. The DDR. Okay, yeah, I see what I did wrong. Okay, so this 1/3 is from here, but the formula for the volume of a cone also has its own 1/3. So this should be over 3. So this will be over 9. Like that. So this will be over 9. This will be over 9. Okay, hopefully now it's fine. Okay, yeah. 2 over 9. Let me just see my calculations again. This is 1/3 pi r squared h. Okay, that's fine. So that's 1/3 dh dt. The derivative of v with respect to r, the 2 comes down, pi r h, and then the third is still there. Okay, when we factorize, we have pi, 1/3 pi r squared plus 2 over 9 pi r h. Okay, and then dh dt is dv dt over 1/3 pi r squared plus 2 over 9 pi r h, and then it's just substituting. The only other thing is the radius here, say 3 r over 3 with 5 over 15. Okay, looks fine. Let me type it in, minus okay, so now I'm getting 0.318, and then our units are in meters per second. Okay, so lots of calculations, very easy to make a mistake. And you can see that if you make a mistake somewhere, it affects everything that goes down. So the reason why it's negative, like I said, is because it is decreasing. And again, that makes sense. If the volume of the water is going down, obviously the height over here in blue is also going down. So we can write this sentence to conclude. Say the depth is decreasing at a rate of 0.318 meters per second. So if I use the word decreasing, there's no need for me to have the minus here. If I say it's changing at a rate, then I'd have to put the minus, which means it's decreasing. So don't use decreasing and then negative at the same time. It's either one or the other. Okay, then the next one, a balloon is inflated at a rate of 10 centimeters squared per second. So with balloons, we assume that these are spherical balloons, so they are round, and they're inflated at a rate of 10 centimeters cubed per second. That's the volume. So dV dt, this is 10 centimeters cubed per second. At what rate does the surface area change when the radius is 5 centimeters? So we're looking for the change in the surface area with respect to time when the radius is 5 centimeters. Okay, so when given a balloon like that, it's getting bigger and bigger. Now, at the point when the radius is 5 centimeters, what is dA dt? That is what we're looking for. So here, again, we come up with our formulas. So we know that the volume of a sphere, this is 4/3 pi r cubed. So you can see in this formula, there's no A, so we will need another formula where we would actually work out the dA dt. So from this formula here, okay, even that, you just also note that the surface area of sphere is given by 4 pi r squared. Okay, so this is the one that we want to eventually differentiate with respect to t and get dA dt. But you can see that when we differentiate this one, we need dr dt. So we can use this formula to work out dr dt. We get our answer and then substitute it over there. So here, dv dt, this is just dv dr. So this time it's a full derivative because the v only depends on r. There are no other variables there. And then multiply by dr dt. So all this we can work out dr dt, and then we'll substitute it over there to get dA dt. So dv dt, what is dv dt? And then dv dr, this is 12/3, or the 3's cancel. So we have 4 pi r squared multiplied by dr dt. So we can make dr dt the subject of a formula, and then work out what it is. Let me just do it over here. So everything, we can see everything. So dr dt, this is dv dt over 4 pi r squared. So I can just substitute because I have the values. dv, let me see. Rates of change, yes, they will be part of the test because they are part of partial derivatives. So the test will include partial derivatives, so this will also be part of the test. So dv dt is given to us over here, it's 10. And then in the denominator we have 4 times pi, and our radius is 5 squared. Okay, so that you would just work out on your calculator. And what do we have? So now we have dr dt. Over 4 times 5 squared. That's 1 over 10 pi. Okay, so I don't round it off because I still need to use it to work out the ADT. Okay, so now that I have that, I go back to the formula for the surface area. This is 4 pi r squared, and the ADT, which is the one I'm looking for, this is given by dA dr. Again, this is a full derivative because you can see that the A only depends on r. There are no other variables. Then I multiply by dr dt. So this is the ADR, that is 8 pi r, and then multiply by dr dt. So now we can substitute. This is 8 pi. The radius that we're given in the question is 5. Yeah, the radius is 5. And then we multiply by dr dt, which is 1 over 10 pi. Maybe I should specify dA dt. Here we have r is equal to 5. So we're looking for it at that particular instant. So it's 1 over 10 pi. And see the pi's cancel. So this is 4. And then our units are centimeters squared per second. So include the units. So we say that when the radius is 5 centimeters, the surface area is increasing at a rate of 4 centimeters squared per second. Okay, so that is how we would answer that. So we will stop here for today and tomorrow look at exercise 2.4. Remember that the test is on Wednesday, the 15th. The time, Mr. TK said 12:30, that's lunchtime. It is a face-to-face test, so you need to be on campus to write it. If you're not in Windhoek, you can send me an email with your details and you can write it at one of the centers, I guess. Okay, so we're almost done with this chapter. The last thing after that is just the maxima and minima, which hopefully by tomorrow we will have covered, and that will be where the test will stop. So this chapter very short, but nothing too complicated there.